Okay, I want to do just one more small video on polar area, and it's kind of like doing washers and top curve minus bottom curve. You have to really be careful on what the problem asks. So let's look at this one. So this R equals 6 sine theta. This is this vertical circle here, so it's the blue. And then this is kind of this cardioid, which is this red curve. We know that polar area is 1/2 r squared d theta. And again, that comes from the fact that we know that no matter if our r value is changing, we just want to keep adding up sectors. And so if we just wanted, let's say, half of this circle, so if we wanted to just do that part of the circle, right, what we're doing is we're taking all of these sectors and we're adding up an infinite number of them. So the area there would be the integral of 1/2 r 6 sine theta squared d theta. And again, if you make your angle small enough, then all of these become the same. So you're finding each one of these little bitty sectors, and we know that the area formula for the first sector is 1/2 r squared theta. Okay, so now we have to do the harder ones. So hard ones when we have kind of two curves. So if you look at these two curves, and again, how do you find them? How do you find their intersection, right? They intersect there and there, and I happen to have those two values listed. So you'd set the r values equal to each other. So you're saying, when does 6 sine theta, when does r1 equals, let's say, r2? Unfortunately, your polar graphing calculator won't, in the polar mode, it won't be able to find those. So you actually graph them. If you can't do this algebraically, then you have to put your calculator back into Cartesian mode and go and graph this is y1 and this is y2, and then find the intersection of those two curves, which your graphing calculator can do, and then you have those two angles. Okay, so let's say we have those two angles, and now I want to find this. Let's say I wanted to find the area inside the circle and inside the cardioid in quadrant 1. So inside both curves in quadrant 1, so I'm talking about this area right here, so right, that area right there, that's what I want to find. And like, okay, well, how do you do that? Well, in this case, you're going to have to do two integrals, because this area is bounded here by the blue and here by the red. So think about that. And the first part of this is you summing up these sectors. And so you'd sum up from 0 to the intersection angle, 0.927 radians. And again, that's like 50 degrees or something, 55 degrees. 1/2 r, in this case, you're going to use the 6 sine theta as your r value, d theta, plus you need to add up these sectors. Well, these sectors are bounded by the red curve. And you can see now I have the area I want. I have this area, which is the area inside the cardioid and inside the circle in quadrant 1. So then I need to integrate from 0.927 all the way to pi over 2, which gives me all that first quadrant area of 1/2 3 plus 3 cosine theta squared d theta. And I add those two areas up, and then you get the red and the blue, and you get everything that I wanted. And again, the blue is kind of the bound, and then the red is the bound, because the two curves are different. Okay, so sometimes you have to add up integrals. Sometimes you just got to do one integral, like here, all you want is that. Okay, now let's find the area in the first quadrant that is outside the circle and yet inside the cardioid. That's this area. Okay, and now we're looking kind of like as a washer scenario. Okay, so what would happen if you just integrated the cardioid from 0 to this angle? Okay, so we integrated from 0 to this angle, we'd get all of this. Okay, so if we integrated from 0 to 0.927 of 1/2 of the cardioid, 3 plus 3 cosine theta squared d theta, we get the whole red. But we don't want this whole red. We just want inside the cardioid but outside the circle. So what do we have to do? Well, we have to subtract this. So we need to take away this area, but that area is the blue. Well, So we need to subtract integrating from 0 to 0.927 of 1/2 the blue, which is 6 sine theta squared d theta. And now we actually have the area inside the cardioid and outside the circle. And so if you think about what this looks like in the abstract, a lot of people, when you have to do this inside-outside thing, that you just want the outside but not this inside, then they're going to say integrate from 1/2 r squared minus r squared d theta from whatever, theta 1 to theta 2. So if you see this formula, it's similar to that washer formula. But you're really just doing the total minus this inside piece, and then you're going to get the outside piece. So sometimes, again, see how the blue curve and then the red curve were the bounds, and so you have to do 2 separate integrals. And then sometimes you have to do 2 integrals and you're going to subtract them because you just want the outside. Now if you just wanted the inside of something, well, that's pretty easy. Then you can just do 1 integral. Okay? Most of the time you're looking at these 3 cases, either 2 separate integrals, 2 integrals because the bounds are kind of an inside and outside one, or you just kind of want 1. And you know, the first step in doing these 2 problems is to find this intersection, right? This intersection is obviously super important. You can't do the problems because you need this bound, right? You need when this hits, and again, the algebra down here is what you do. Okay, I think that's really it on polar. All the other stuff is kind of more related to just calculus, you know, finding dy dx, dr d theta. It's just a lot of derivatives, but the area gets a little tricky and the intersection gets a little tricky, but just take your time.